Hello everyone, welcome back to my channel. My name is Abhinav Sharma and I'm currently pursuing BE from Sri Venkateshwara College of Engineering. Today, we will see the use of superconductivity of metals in the field of quantum computing. So what is superconductivity? Superconductivity is a set of physical properties observed in certain materials where electrical resistance vanishes and magnetic fields are expelled from the material. Any material exhibiting these properties is a superconductor. Unlike an ordinary metallic conductor, whose resistance decreases gradually as its temperature is lowered, even down to near absolute zero, a superconductor has a characteristic critical temperature below which the resistance drops abruptly to zero. An electric current through a loop of superconducting wire can persist indefinitely with no power source. How does superconductivity works? When normally conductive elements and compounds with electromagnetic properties are cooled to low temperatures, they display two important properties of superconductors. They present no resistance to an electric current and they generate a magnetic field. Thus, they enter a superconducting state. Since the discovery of superconductivity, research has identified many materials that can be turned into superconductors. However, the transition temperature varies for each material. A key challenge has been to develop materials that become superconductors at higher temperature than absolute zero. Many materials, both single element and compound elements, have demonstrated high temperature superconductivity. This makes it easier and more cost effective to employ superconductors in a variety of applications. How are superconductors used? Superconductors have been used in or proposed for use in a wide range of applications. Examples include high-speed magnetic levitation trains, magnetic resonance imaging equipment, ultra-high-speed computing chips, high-capacity digital memory chips, alternate energy storage systems, radio frequency filters, radio frequency amplifiers, sensitive visible light and infrared detectors, miniaturized wireless transmitting antennas, systems to detect submarines and underwater mines, and gyroscopes for Earth orbiting satellites. The Josephson junction and superconducting quantum interference device use superconductors. Superconducting quantum computing. Superconducting quantum computing is a branch of solid-state quantum computing that implements superconducting electronic circuits using superconducting qubits as artificial atoms or quantum dots. For superconducting qubits, the two logical states are the ground state and the excited state. Research in superconducting quantum computing is conducted by companies such as Google, IBM, IMEC, BBN Technologies, DJT, and Intel. Many recently developed QPUs or the quantum processing units of quantum chips utilize superconducting architecture. Superconducting quantum bits. The idea of superconducting qubits is at least several decades old. It got more traction at the turn of the century when it was demonstrated that they are, in fact, physically possible. It was shown that the 0 and 1 states could be measured, as well as the superposition between them. Even though the qubits back then were pretty lousy, maintaining their superposition for only a brief period, it was a significant achievement that created a lot of interest around the approach. Superconducting qubits, at their very core, are electric circuits. There are different types of superconducting qubits that all have same fundamental characteristics. The usage of superconducting materials being one of them. Another common feature is the utilization of so-called Josephson junctions. These are points in the superconducting material that do not allow the classical flow of electricity through them. However, due to the phenomenon of quantum mechanical tunneling, electricity does flow through the junction in tiny amounts. As this junction resists the flow of electric current depending on the total amount of the current, the junction's behavior is nonlinear. In an electric circuit, the inductance and capacitance usually do not depend on the oscillation amplitude, whereas with the Josephson junction this is the case. This means that the value of the inductance has a nonlinear dependence on the amplitude of the oscillation, creating a nonlinear electrical circuit. This enables differentiating between different electrical states, characterizing the 0, 1, and 2 as the properties of the circuit change during the transition of one state to another. Importantly, we can measure these changes between the states. Advantages and disadvantages. One of the advantages of working with superconducting qubits is that we can design the electrical circuits to carry out the kind of the dynamic we want. This is possible due to the fact that we can mass produce circuit elements, allowing us to test different designs to see what works best. This process is one of the key drivers of the steady achievement made in the circuit's quality and design. In fact, we might currently be relatively close to the point where the design itself is sufficient, allowing us to expand to a larger number of qubits. This advantage, though, doesn't come without a flip side. When mass producing, no one circuit is similar at the atomic scale, which causes differences in the behavior of circuits and decoherence in the qubits. Furthermore, the usage of bulk materials carries some faults as these materials can contain impurities that then cause more decoherence in the qubits. Currently, this is just the price to pay for being able to test with different designs and compositions. There are many ways to face this problem, though, the most simple of them being better material and enhancing the manufacturing processes. Likewise, new designs can also do their part in minimizing decoherence, and this is where modeling and simulations are key. For example, accurate electromagnetic simulations over a wide range of length scales are pivotal. Decoherence will, however, always be prevalent. Therefore, the realistic goal is not to eliminate the decoherence, but to instead minimize it so that it doesn't restrict the qubit performance excessively. Challenges of superconducting quantum bits and future prospects. When it comes to choosing the right path or the correct physical implementation for qubits, no one knows the right answer. To seek guidance, we may look at the history to see superconducting qubits offering steady development for more than 20 years. Compared to other implementations, superconducting qubits seem to have a more reputable background that could give hope for future advancements. But as stated before, any technology is proven to provide useful quantum advantage, no one knows for sure. Examples of superconducting quantum computers. Several companies and institutions have developed and demonstrated superconducting quantum computers using different types and numbers of superconducting qubits. Google, which has claimed to achieve quantum supremacy, the ability to perform a task that is infeasible for a classical computer, using a 53-qubit processor called Sycamore. IBM, which has launched a cloud-based quantum computing service called IBM Q that allows users to access various quantum processors ranging from 5 to 65 qubits. Rigetti, which has developed a hybrid quantum classical computing platform called Rigetti Quantum Cloud Services that combines a 32-qubit processor with a classical computer. Applications of superconducting quantum computing. Superconducting quantum computing has potential applications in various domains, such as cryptography, as it can enable the implementation of quantum key distribution, a secure method of exchanging encryption keys, and quantum algorithms such as Shor's algorithm, which can factor large number and break some classical encryption schemes. Optimization, as it can solve complex problems that involve finding the optimal solution among many possible options, such as the traveling salesman problem, the knapsack problem, and the quadratic assignment problem. Machine learning, as it can enhance the performance and efficiency of artificial intelligence techniques, such as classification, clustering, regression, and reinforcement learning. To conclude, superconductivity achieved at low temperatures eliminates electrical resistance and magnetic field penetration, offering opportunities for efficient energy transmission and groundbreaking technologies. Superconducting qubits, leveraging superposition and entanglement, signify a quantum leap in computing potential, enabling simultaneous states and propelling us towards advancement quantum computation. The convergence of superconductivity and quantum bits holds transformative potential, promising to revolutionize computation by addressing complex problems in cryptography, optimization, and material science. So that's it for the use of superconductivity in the field of quantum computing. Thank you.